In section 14.1, we introduce multiple integrals over rectangular regions. That is where our two sets of limits of integration were constants. In 14.2, we're going to introduce double integrals over non-rectangular regions, which means we're going to begin introducing non-constant limits of integration. In this first remark here, we say that it's okay to have non-constant limits of integration. We're going to evaluate those integrals in the exact same way that we did in 14.2. Now, one thing that I want to notice is our outer integral here, which I just highlighted, should always have constant limits of integration. So there should be no variables allowed in that outer integral. However, our inner integral is allowed to have variables in those limits of integration. The variables allowed should correspond to what you want to end up integrating in your second iteration. So in this first integral, you'll notice that we'll have limits of integration that are in terms of x. That's because our second iteration is going to be an integral in terms of x. And then similar in the second one, we have limits of integration in terms of y because our second iteration will be an integral in terms of y. So we're going to jump right into our first example. You'll notice that in problem 6, the integral is already set up for us, including those limits of integration. And so we just want to carry out the integration. If you want, you can input a set of brackets here that tell you that you're integrating with respect to y first. So when I look at this x squared term, it's considered a constant. So when I integrate it with respect to y, I'm going to tack on a y variable. I'm going to begin by recopying my first integral, and then I'm going to write this as an x squared y. Then integrating y as usual, I have a 1/2 y squared. Now, I want to evaluate this from negative x squared to x squared, but because I have two variables involved here, I'm going to specify that I'm evaluating y from negative x squared to x squared. And then once I'm finished with that, I will be integrating with respect to x. All right, so applying the fundamental theorem of calculus, I'm going to evaluate at my upper limit of integration, which is positive y squared, gives me x to the fourth minus 1/2 x to the fourth. And now I'm going to subtract off evaluating in at negative x squared, which gives me negative x to the fourth minus 1/2 x to the fourth. All of this being integrated with respect to x. So I see some cancellation here with the fractional x to the fourth terms. And once I simplify, I have the resulting integral from -1 to 1 of 2x to the fourth dx. At this point, this is just a standard integral from Calc 1, and I'm going to integrate it accordingly. I have 2/5 x to the fifth from -1 to 1, which gives me 2/5 minus a -2/5 for a total of 4/5. All right. So as you can see, the process of carrying out the integration really is no different than it is in 14.1, the only exception being that we're plugging in variables rather than numbers. The tricky part about this section is not the integration, but is actually setting up the integral, and in particular, finding those limits of integration. And so our remaining examples are going to be practicing this technique of taking a problem, identifying the region that we're integrating over, and then finding those limits of integration accordingly. In order to do that, we need to understand the two different types of regions that we'll be working with. So this following definition identifies these two regions. So we're going to call a region type 1 if it's bounded on the left and the right by vertical lines x equals a and x equals b, and then bounded above and below by continuous curves g sub 1 and g sub 2 of x. Here we're assuming that g1 is always bounded above by g2 as x approaches from a to b or progresses from a to b. So let's sketch just a little diagram here of a type 1 region. And I'm just going to sketch these two types of regions down below here in the margin. So you can see I have numbered 1 and 2. So I'm just going to draw some coordinate axes. And then along your x-axis, just label A and B. And so for our region, we want to have it bounded by vertical lines at A and B, maybe right here, and then continuous curves on top. So I'm going to call this G2 of x, and on bottom, G1 of x. All right, so this region that's enclosed by these solid lines, x equals a, x equals b, and the two continuous curves, G2 of x and G1 of x, is going to be called a type 1 region. For a type 1 region, we're going to want to be taking really, really tiny slices that are vertical distance, because when we stack those up next to each other, they'll stack nicely with these straight sides, all right? And so we'll see that here in the next theorem. But then back up to the definition, a type 2 region is bounded above and below by horizontal lines, y equals c and y equals d, and then it's bounded on the left and right by continuous curves, x equals h1 of y and x equals h2 of y. Notice how these continuous curves are now solved for as x as a function of y, as opposed to what we had in the type 1 region. So let's draw a little diagram for this type of region. So along the y-axis, choose your C and D values, and we're going to have horizontal lines there. And then we want continuous curves on the sides. Okay, so here's our continuous curves. On the left, we have x equals h1 of y. On the right, we have x equals h2 of y. All right, and then here's our region in between. So when we're going to be working with regions of type 2, we're going to be taking horizontal, really small slices, computing those areas of those rectangles, and adding them up by way of an integral. And again, it makes sense in this way because those horizontal slices are going to begin at a straight horizontal line and end at a straight horizontal line as we stack them up. And so theorem 1 here is stating exactly that. Depending on the type of region, we're going to identify the order of our integration. Are we going to integrate x first and then y, or y first and then x? And so this is what this theorem is stating. Part A says, suppose you have a type 1 region. So we're looking in this first picture. Then what I want to do is I want to take a look at one of these strips that I've drawn. So let me color one of these in red. All right, so here's one of our strips. You'll notice that it doesn't have very much thickness. It's supposed to be an infinitesimally thin strip, which means if I'm calculating its area, I'm going to call that thickness dimension dx because it's in the x direction. Now, when I look at the height from top to bottom, that's where it starts getting interesting. The top is governed by G2 of x, the bottom is governed by G1 of x. So you'll see those values here in the inner integral for those limits of integration. And then that thickness is always at the end of your integral. So you'll notice that dx thickness occurs here. So that tells you that you want to end in the x variable because you want to go from A to B along your x-axis. So you'll see me oftentimes sketching these regions and then showing a little strip, whether it be vertical or horizontal, and identifying that thickness, in this case dx, That tells me that I want to integrate with respect to x last and with respect to y first. Similarly, part B of this theorem says that if you have a type 2 region, now you're doing a little horizontal strip, and your thickness of your horizontal strip is in the y direction. So we have a dy there. That's occurring at the back. Your horizontal lines from y equals c to y equals d are going to govern your limits of integration in y. And then, of course, we just have those bounding functions h1 and h2 serving as our limits of integration on the inside. All right, so let's practice setting up integrals using this technique, beginning with number 20. All right, evaluate the integral. We have an integrand x cosine y. You'll notice that our differential here is dA because we're going to have to decide if we want dy dx or dx dy. And here R is the triangular region bounded by the lines y equals x, y equals 0, and x equals pi. In these types of problems, it is 95% necessary that you draw the region involved because without that region really physically drawn, it's nearly impossible to identify your limits of integration. So I'm going to draw this region over here. And your sketch doesn't have to be super accurate, just needs to be accurate enough so that you can see how you're going to set up those limits of integration. So here's my line y equals x. Then I have the line y equals 0, which is the x-axis. And I have the line x equals pi. All right, and so then I'm just going to shade in the region that's bounded by those three lines. All right, and so here's the triangular region R. The question is, what type of a region is this? This is kind of a unique setup here because we don't have vertical lines bounding on the left and right, and we don't exactly have horizontal lines bounding on the top and bottom. We kind of have a combination of both. So this is a unique example where we could choose to set up our integral in either fashion, but the choice that we make is going to govern how we're going to set up our limits of integration. So I'd actually like to solve this problem twice, once using a type 1 region and once using a type 2 region. So let's start out here with method 1. And this will be assuming a type 1 region where we're going to set it up as dy dx. All right. So if we're going to consider this as a type 1 region, we're going to take vertical slices. All right. So here's one of our little rectangles if we're thinking back to Riemann sums from Calc 1, and we want to add up all of these rectangles, and that's exactly what an integral does, right? It adds up a bunch of rectangles. In this case, our thickness is in the x direction, so we have a dx thickness. So that means that our outer integral is going to be in terms of x, and our inner integral will be in terms of y. So I'm going to recopy my integrand x cosine y, and because I decided to take vertical strips, that's going to be of the form dy dx. Now, the x limits of integration are going to be the easy ones. You just look along your x-axis and you see what your smallest and highest x value can possibly be. The smallest x can be is at this point, which is at 0, and the largest x can be is at this far right point, which is at pi. So again, I cannot stress enough, your outer limits of integration will always be constant. There should be no variables in there. Now, your inner limits of integration are referring to the top and bottom lines or curves that are bounding your region. So our top curve is y equals x, and our bottom curve is y equals 0. So when we're looking at our strip, we're going from y equals 0 all the way up to y equals x, and those are going to serve as our limits of integration. Again, I want to note here that these variables should be in terms of x because our ending integral will be in terms of x. Okay, so now we have our integral set up. Now we just need to carry out the actual integration. X is going to be considered a constant in this first integral iteration, and so we need only integrate cosine of y, which integrates to sine of y. So I'm going to copy my outer integral from 0 to pi. X just tags along. The integral of cosine is sine. And I want to evaluate sine of y from y equals 0 up to y equals x, and then integrate that remaining function in terms of x. I know that sine of 0 is 0, so that just drops out, leaving me with the integral from 0 to pi of x sine of x dx. Unfortunately, we can't integrate this directly, so we need to think back to our techniques of integration that we worked really hard to build in Calc 2. So when use substitution and direct integration fail, when we see a product, as we do here, an x and a sine of x, that is a tip-off that you want to use integration by parts. And so if you'll recall, we had an acronym to help us choose u, and the acronym was LIPIT. And those letters stand for logarithms, inverse trig functions, polynomials, exponentials, and trig functions. And those are listed in decreasing order of what you want to choose for u. So for example, if you ever have a logarithm in your product, that's going to be your first choice for u. When I take a look at my two terms here, I have x, which is a polynomial, and I have sine x, which is a trig function. So you can see in the decreasing order that Lipit gives us, the polynomial wins out. So I'm going to let u be x, which seems kind of silly because we're just trading all x's for u, but bear with me here. And then I'd like to set up my dv, which is going to be everything that's left over after I've chosen x. So that's going to be sine x dx. And then we'll fill in our grid. I need du, which is going to be dx, and v, which is just going to be the integral of sine x, which is going to be a negative cosine x. Now, if you'll recall, we're not going to worry about the plus c here. We worry about that once we've carried out the integration by parts. And so the integration by parts formula, in case you forgot, is the integral of u dv is uv minus the integral of v du. All right, and then if we have limits of integration here from a to b, they still carry on here in your integration by parts formula. So now that we have it set up, I get uv, which is a negative x cosine x, minus the integral of v du, negative cosine x dx. Now again, we had limits of integration from 0 to pi, so I'm just going to add those in here. And so when we look back at where we started, the integral of x sine x, and the integral that resulted in by parts, we see that we have an easier integral that we can just integrate directly. So a couple of things here. First, I'm going to take care of the double negative, and I'm going to turn them into positives. Next, I'm going to go ahead and evaluate. Notice that this function is going to drop out at 0 because of plugging in 0 for x. So I'm just going to plug in pi. Cosine of pi is -1, so that double negative turns to a positive. So I have just a positive pi here. And then let me go ahead and integrate cosine. The integral of cosine is sine. And I want to integrate sine from 0 to pi, but that entire function is going to die out because sine at 0 and pi is both 0. So our final answer here is pi. All right. Now let's go ahead and evaluate this integral using the other method, assuming a type 2 region. Of course, we should get the exact same answer. So we should conclude that we're going to have an answer of pi. All right, so if we're using a type 2 region, we're now going to draw our strips horizontally. And we're going to note here that our thickness of our strip is now in the y direction. So again, I like to note that because I like to remember that that thickness is going to be our outer differential because we're going to integrate with respect to y at the end and get our constants that way. So our integrand isn't going to change. It's still x cosine y. But because my thickness is in the y direction, now I'm going to integrate x first and then y. All right, so now we want to think, what are our highest and lowest y values? Certainly our lowest y value is y equals 0, right? So we get to 0 on the y-axis. And then what's our highest point y? It's right here, right? Here's our highest point on the y-axis. This vertical line here is at x equals pi, and since our equation is y equals x, this is the point pi pi. So I know that this value on the y-axis is pi. So it just so happens that our outer limit of integration is the same as it was in method 1. That won't always be the case. It was the case specifically because the line governing here, the hypotenuse was y equals x. So we got pi in both dimensions. All right, so now let's figure out what our limits of integration for the inner integral should be. When we think back to the strip, we want to figure out what that upper boundary line is and what the lower boundary line is. So what we see is on this far right side, we have the equation y equals or x equals pi. On the left side of my strip, I have the line y equals x, which again seems silly, but I'm going to write it as x equals y. So let me highlight those two. I have x equals y and x equals pi are governing my rightmost and leftmost boundary line. So the rightmost line is going to serve as our upper limit of integration, x equals pi. The leftmost boundary line is going to serve as my lower limit of integration, which is x equals y. Again, making sure that these limits of integration are in terms of the y variable, because we will want everything in terms of y once we get to that second iteration of integration. All right, so now we're ready to integrate. First, I want to integrate with respect to x. So this cosine of y term is just a constant. I'm just going to bring it along. I'm going to copy my outer integral, and then I'm just going to integrate x. So x becomes a 1/2 x squared. My cosine y just gets recopied, and I want to evaluate my x term from y to pi, and then recopying that outer differential dy. All right, and so let's go ahead and evaluate our limits of integration. So plugging in pi first gives me a 1/2 pi squared cosine of y. And then evaluating at y next, I have a 1/2 y squared cosine of y. All right. So for this first term here, I can integrate this directly. The 1/2 pi squared is a constant, and the integral of cosine y is sine y. So I have a 1/2 pi squared sine y from 0 to pi. And I'm just going to note here that this entire term is going to die out just because sine of pi is 0 and sine of 0 is 0. So we get nothing new from this piece. However, we still have our other piece to integrate. So I'm going to write that over here. And actually, maybe I'll pull the 1/2 out front, though it doesn't particularly matter. I have y squared cosine y dy. All right, so this one is a little bit troubling just because we see the product of a polynomial and a trig function, very similar to what we had up here in method 1. But the reason why I say this is troubling is because our polynomial is degree 2. This is indicative of the fact that we're going to have to use integration by parts not once but twice. So this right here shows you that maybe method 1 is preferable over method 2, even though we'll get the same answer either way. All right, so let's carry out the integration by parts. The first iteration, I'm going to use u1 and dv1 because I'm going to have to do this twice. Using Lipit, I'm going to let my polynomial be my u, so that's y squared. So du1 is going to be a 2y dy. And then everything that's left over is dv1, so cosine y dy. The integral of cosine is sine. And so now let's carry out the integration by parts. I'm going to leave my negative 1/2 out front. Oh, and I did forget to carry over my limits of integration, so I'll add those in. And so I have uv, which is y squared sine of y. Remember to use those same limits of integration, minus the integral from 0 to pi of v du. So I have a 2y sine of y dy. All right. So once again, we see that this first term is heading to 0 because we're evaluating sine at pi and at 0. Now, let me distribute this negative 1/2 to this second integral. You'll notice that I have a double negative, which makes it plus, and 1/2 times 2 is 1. So what I'm left with here is the integral from 0 to pi of y sine of y dy. Now, if I wanted to, I could carry this out with a second iteration of integration by parts. But look, if I zoom out here, this is the exact same integral that I had up here, with the only difference that the y's are x's. But even our limits of integration are the exact same. So I'm going to bypass all of this, and I'm just going to say, look, I've already computed this integral, and it was equal to pi. So I'm just going to say that this is equal to pi, and I'll make a note here, by above work. No need to reinvent the wheel. We've already solved that integral up above. All right, so again, kind of looking back, both of these methods are completely reasonable. Sometimes it'll be clear which method is better than the other. Other times it's not as clear. In this case, the integrand was fairly simple, so it didn't really make a difference whether we wanted to integrate with respect to x or y first, so that didn't really help us choose which method to use. But once we got into the two methods, we saw that method 1 was easier just because we didn't need an integration by parts twice. All right, we have just 2 more examples in this section. But first, a remark says that the area of a region R in the xy plane can be found by evaluating the integral of 1 dA over your region R. So this is telling us an application of a double integral is that we can compute the area of a two-dimensional region. So using this idea here, let's compute number 30. Use double integration to find the area of the plane region enclosed by the given curves. All right, so here again, I find it almost absolutely essential to plot your region that's being defined by these curves so that you can identify which way to set up your limits of integration and your um, order of integration. So we're going to start here with a parabola. Notice that we have it of the form x equals y squared, not y equals x squared. So it's a sideways parabola. The negative means it's going to be opening to the left. So if I sketch that, when x is 0, y is 0. Okay. When y is plus and minus 1, x is negative 1. When y is plus and minus 2, x is negative 4. So I'll just go out one more. When y is plus and minus 3, x is negative 9. So 5, 6, 7, 8, 9. Okay, so here's a somewhat accurate sketch of that parabola. All right, next let's sketch the line. I'm going to transform it into y equals mx plus b. So I have 3y equals x plus 4. So y equals 1/3 x plus 4/3. All right, so our y-intercept is somewhere around here. You'll notice when x equals negative 1, y becomes negative 1/3 plus 4/3 is 1. So we intersect at this point negative 1, 1. And then you can sketch it from here, quite honestly, if you want to. And you can see that there is some type of a region in between this line and this parabola. Now, what we don't know, because I'm not going to assume that I drew this super accurately, is where is this point of intersection? We did figure out this upper one here just kind of by dumb luck, but we didn't figure out the other one. So what I'm going to do here is I'm going to solve this system of equations. And what I'm going to do is I'm going to say, look, I know that negative x is y squared. So I'm going to plug that in for negative x right here. So I'm going to show this work down below this sketch. This gives me 3y plus y squared equals 4. So let me move everything to one side. Y squared plus 3y minus 4 equals 0. And then I can factor to y plus 4, y minus 1. And so I get two y values. I get y equals negative 4 and y equals positive 1. Now we already knew this one. We didn't know this one. So if I plug this back into the equation for x, remember x equals negative y squared. So then if y is negative 4, x equals negative 4 squared, which is negative 16. So you can see that my graph is fairly off here. This intersection point is the point negative 16, negative 4. And then we already labeled this upper intersection point. It's important to find these intersection points because we're going to need to know the highest and lowest values in order to identify our limits of integration. So I wanted to do that first and foremost. All right, so next the question is, do we want to take vertical strips or do we want to take horizontal strips? So let's investigate this. If I drew a little strip right here, a vertical one, all right, so what I have is my upper boundary curve is going to be actually the line, and my lower boundary curve is the parabola. So that's all great and well, but as I continue to move my strips over to the right, once I pass this intersection point here, Now my vertical strip that I just drew has a different upper boundary curve. Namely, it's that parabola on top and on bottom. So this is bad because if I was going to do my integral with vertical strips, I would have to break it up right here at this intersection because my strips to the left of that big red line have a top boundary line of y equals 1/3 x plus 4/3 and a bottom boundary line of the parabola. And then on the other side, my upper and lower bounding curves change. So because of that, I'm going to delete these and I'm going to say, you know what, maybe vertical strips isn't my best bet. How about a horizontal strip? So when I look at this horizontal strip, on the right of my strip is the parabola. On the left of my strip is the straight line. And no matter where I move this horizontal strip, even if it's really high up, it's always going to have the same boundary curves on the left and on the right. The left is going to be the line, the right is going to be the parabola. So this is an indicator that I want to use horizontal strips. So in moving forward with that method, I'm going to notice that my thickness is in the y direction, which means I want my dy differential on the outside. All right, so as a way to begin, I have my double integral. I'm trying to find the area of the region, so I'm just going to integrate 1. And then my dA, I have just determined is going to be dx dy. Again, that dy differential being on the outside because that's the thickness of my strip. All right, let's do the outer limits of integration because they're the easiest. I just want to find how high and how low my y values can go. And so the highest y can be is right here at the top of this, where we had the intersection at y equals 1. And then my lowest y can be is down here at y equals -4. So this is just picking off those y values in the intersection points, which we had found right here. All right, so now the tricky things here are going to be finding our inner limits of integration. And those are just going to be the two sides of my strip. Okay, so we're always going to do right on top and left on bottom. So what is my right bounding function? My right bounding function was y squared equals -x or x equals -y squared. I want that limit of integration in terms of y. So my upper limit of integration is a -y squared. And what about my lower limit of integration? That's coming from this line, but I want to solve x in terms of y. So take a look at this equation, and we can say that x equals 3y minus 4. That's going to be my lower limit of integration. All right, so this is, in my opinion, always the hardest part, is setting up your limits of integration. Typically, when I'm grading these types of problems, I give you half credit for the problem if you only set it up correctly. I say only, but really that's where the challenge is. Look at all the work we just spent just getting to the setup of that integral. We had to draw the region. We had to find where those lines and curves intersected, and then we had to go through the geometry of the section to identify the order of integration and how to set up those limits of integration. Quite frankly, at this point, the integration is the easy part. So let's move forward. I want to integrate 1 with respect to x. So that's going to give me an x, and I want to evaluate x from 3y minus 4 up to -y squared dy. And so that's going to give me the integral from -4 to 1 of -y squared minus 3y minus 4. All right, so we're down to a Calc 1 integral. This is going to give me a -1/3 y cubed minus 3 halves y squared. Remember to distribute that negative to the 4. It becomes positive 4y from negative 4 to 1. And now just plug in all of your values using the fundamental theorem of calculus. So when I plug in 1, I have negative 1/3 minus 3 halves plus 4. And now I'll plug in negative 4. So negative 4 cubed, 4 times 4 is 16, times 4 is 64. But I have a quadruple negative. So it becomes a positive 64/3. Next, I have 16 times 3, 18, carry the 1, 48. So I have 48 halves. I'm just going to write that as 24. And then finally, 4 times 4, I have a negative 16. All right. Quite frankly, if you just boxed in this answer, I'd give you full credit on a quiz or an exam, but I'll go ahead and simplify. This is negative 65/3 if I combine these two. All right. Distribute this negative here. This all becomes positive 40 plus another 4 is positive 44 minus 3 halves. So this is 44 plus, let's see, what are we going to get here? 165 times 2 is going to be a negative 130, and 3 times 3 is 9 over 6. So I have 44 minus 139 over 6. And so that's going to be, let's see, 44 times 6, 24, carry the 2, 24, 26. 264 minus 139, which is going to give me a total here of 125 over 6. All right, so there's my final answer, but I would have given you full credit right here at this point, even if you just didn't want to carry out the arithmetic, would have been perfectly fine. All right. So again, the takeaway from this problem is that you can compute the area of a planar region using double integrals, keeping in mind that your integrand is always going to be 1 in that case, and then setting up your limits of integration based on the geometry of your region and whether it makes sense to take vertical strips or horizontal strips. All right, so we have one more example here at the bottom of the page. Use double integration to find the volume of the solid. This is going back to what we learned in 14.1. When we introduced multiple integrals, we said that the geometry that's lurking behind the double integral is that the double integral is finding the volume underneath a surface over your region R that you're integrating over. So in one dimension, the analog is that the single variable integral computes the area under the curve from A to B, where A to B are your limits of integration running along your X or Y axis. Up a dimension, instead of area, we're computing volume. So if I want to find the volume of this solid, I need to identify what my upper surface is first. And so this picture here tells us that our upper surface is defined by this equation. Now we need to solve for the z variable. And so I'm going to say that z squared equals 4 minus x squared. And normally when I would take a square root from both sides, I would be very careful about writing the plus or minus. However, notice that we're in the upper half space, so we're in positive z values. So I'm just going to solve this for the positive z. Z equals the positive square root of 4 minus x squared. This expression is going to serve as our integrand. So when we're setting up volume double integrals, the integrand is always the surface that's bounding the volume that you're trying to find. So what I have so far is I want a double integral of 4 minus x squared dA. And so now what I need to do is I need to figure out what this region is that I'm integrating over. So now what you want to do is you want to take this solid and you want to project it down onto the XY plane. So I'm not an artist, but pretend that you're taking your foot here. Here's your shoelaces, and you're stomping down on this region and you're flattening it to 2 dimensions. So what is it going to flatten to? What it's going to flatten to is what you're seeing here in the XY plane. This right here is going to serve as your region R. So what I like to do when I'm working out these problems is I like to draw a separate 2-dimensional sketch of the region. So what I'm going to do is I'm going to take z equals to 0. That's what it means to flatten down to the xy axis. All points in the xy axis have a z coordinate of 0. So what happens here is we end up with this quarter circle that intersects the x and y axis at 2. And this semicircle or this quarter circle is governed by x squared plus y squared equals 4. All right, now I get a choice here. Do I want to do vertical strips or horizontal strips on this region? Honestly, you can do it either way. If I get the choice, and if it doesn't make a difference, it doesn't make my integration any harder, I choose to do vertical strips because it just seems more natural to me for whatever reason. That's the way my brain works. So that means that I'm going to have a thickness in dx. That tells me that I'm going to set up my limits of integration and my order of integration in the following way. So here's my integrand, 4 minus x squared, square root. I want my dx to be at the end. So I'm going to go dy dx. Along the x-axis, the smallest my region can be in the x-axis is 0, and the largest is 2. So those limits of integration are from 0 to 2. And then for my inner limits of integration, I need to figure out what my upper and lower boundary curves or lines are. Now, along the bottom here, this is the x-axis, which is y equals 0. My upper curve is governed by the circle equation, but I want to solve for y in terms of x because remember, my final integration is going to be in terms of x. So this gives me y squared equals 4 minus x squared. Again, taking the positive square root because I'm looking at positive y values, y equals the square root of 4 minus x squared. All right, now I should also mention that doing vertical slices was definitely a good choice here because I don't want to integrate this integrand with respect to x first because I can't do a u substitution. And I would end up having to do, God forbid, a trig substitution. So integrating with respect to y first is definitely beneficial because there are no y's in my integrand. And so I can integrate that directly. All right, so let's carry out the integration. I have my outer integral from 0 to 2. I have no y here, so I'm going to carry forward my square root of 4 minus x squared. And then when I integrate with respect to y, it's going to give me a y. I want to evaluate y from 0 to the square root of 4 minus x squared. Oops, and then I have a dx here at the end. Now, of course, when I plug in 0, that's going to give me a 0 back out. And so finally, I'm just going to plug in my upper limit of integration. And so when I plug that in, I have the integral from 0 to 2 of the square root of 4 minus x squared times the square root of 4 minus x squared dx. And so thankfully, those square roots cancel. I end up with the integral of 4 minus x squared, and I can integrate this directly. 4x minus 1/3 x cubed from 0 to 2. 0 drops out, and in the end, I get 8 minus 8/3, which gives me 16/3. So this concludes our notes for 14.2, double integrals over rectangular, non-rectangular regions. And in 14.3, we will get started with double integrals in polar coordinates.